Today on Venodilodon, I want to go over an interesting phenomena of which I did and saw several years ago, and that was the ability to use an infrared and red laser to remove the glow from different phosphorescent materials. Now, back when I posted up the original video and asked for feedback from the community, I had no idea what was going on. And there was an interesting article that was linked through one of the comments that talked about the interaction between infrared light and different phosphorescent materials. However, I can do this with more than the infrared wavelengths. As I said, in the original video I used a red laser, and in this video I'll be using different lasers as well. Now, I did not find that article to be exactly a full explanation of what was going on. But like any other science-minded person, I went out and started to do my own experiments, and some of those experiments I'll do for you in this video. So let me explain to you exactly what I have set up here for experiments. I have some zinc sulfide stars. There are 3 of them. And I have one that I'm going to be using for a control. And one on a thermoelectric cooler stack. I'm going to be cooling this star to a very low temperature. And one I have here on a 10-watt resistor. And I'll be heating up that star to a higher temperature than normal. I also have some glow powder in here. This is europium doped strontium aluminate. And I'll be putting that in these 2 CPU lids. Now, the upside is that this material can withstand a much hotter temperature than the plastic, so we'll be able to play around with it in a wider temperature range. I have 2 LED flashlights here. One is near UV at 405 nanometers. The other one is UVA at 365 nanometers. I have a couple of lasers. I have one that's 808 nanometers, one that's 405 nanometers, a red that is in the 638 nanometers, 525 nanometer green, and 450 nanometer blue. And they're all above 500 milliwatts. The whole setup here is to show the difference in behaviors in the phosphorescent materials when they're heated and cooled. So let's start the experiments. So first I'm going to turn on the thermoelectric cooler stack, and I am going to start raising the temperature of the resistor. That way we have a hot and a cold star. Hopefully I won't melt that one like I did in a earlier run of the experiment. I'm also going to put the europium doped strontium aluminate glow powder in these 2 CPU lids while the temperatures get to where I want them to be. The other thing I'll be doing is working in the dark, obviously, since I'll be working with glow-in-the-dark materials. So keep in mind that the video quality may suffer because of that. And none of this is scripted, so the science will just end up doing itself. Alright. Oh, those are slidey samples, aren't they? Oh, that'll work. Put the rest of the glow powder into the bottle. Oh, that stuff gets everywhere. Alright. First I want to go over the original phenomena. So I'm going to turn off the light. And we can see a whole mess of different glows. Definitely a better glow with the strontium aluminate stuff than the zinc sulfide stuff. the zinc sulfide stars fade away really quickly. So I'll show you the original phenomena that I did. I'll pick up the infrared laser, and what I'll do is I'll hold the near UV light bulb, and I'll shine the infrared laser onto the glow-in-the-dark star. You'll see that there's a dark area that goes where the laser is. And this happens with the cold star and the hot star as well. But it gets better. So what I'm going to do is I'm going to charge up all of these stars, and we'll wait till they dim out a little bit. Check the temperatures. That's getting there. Let's do that a little hotter. Alright, so I'm going to charge up those stars. We're going to wait till they dim out. We're going to have a little fun with them. So, all the stars dim out at about the same rate, but not for the same reason. And I'll explain a little bit in a second of what I mean by not the same reason. Wait. Alright, now you notice that the hot star is the one that's the dimmest, and the cold star is the one that matches the control pretty much evenly. But here's the interesting thing. What I'm going to do is I'm going to swap the position of the hot star and the cold star. So watch what happens when I put the cold star on the hot plate. The star that was cold begins to glow again. So now what's going on? Well, I can charge up all the stars with the black light, and the control dims out just because it loses that energy. However, the hot star loses that energy quicker. Meanwhile, the cold star holds onto that energy. Now, energy that's not being released ends up being stored, and when it's heated up again, that energy can be released. So, as I said, there's a big difference between how the stars behave when there is a difference in temperature. Now let's go on to the strontium aluminate. We'll put those samples on the hot and the cold. I'm going to grab that. So here's one on the thermoelectric cooler, and that'll be cooled down. And we're going to put one on the little resistor hot plate. Now we notice that the one that's cooled is getting darker, and the one that's heated is getting brighter. So I'm going to take and I'm going to charge those up again. And we'll see that change. The one that's cold will end up going dimmer and dimmer. Meanwhile, the one that's hot will be the one that shows a higher persistence of output. And the same thing, if I take the infrared light, they behave very differently. You can see that the infrared on the cold one shows up more of a brighter green, and the infrared on the hot one barely shows up at all. Another interesting thing to note is that I can remove the glow on the cold one, but I can't remove the glow on the hot one. So, once again, there's another behavioral change. I'll charge those up again. You'll also notice that the one that's cold doesn't emit a charge pretty much at all. And once it's cold, it doesn't want to give up that glow. It wants to hold on to that energy because the molecules are colder, they're less active, and because of that, the output is significantly reduced. Now I'm going to do the same thing as I did with the stars before. I'm going to swap the positions of the cold and the hot one after they dim down a little bit. And you'll notice that the output will be released from the cold sample and it'll be very bright. So wait a little bit. It's a really good glow powder, so it's going to take a little while. I think I'll swap them now. And you'll notice that the one that was cold will end up being the brighter one. So temperature does play a huge role in the changes of behavior with the different phosphorescent material. The hotter the material is, the quicker it releases the energy, and the colder the material is, the slower it releases the energy. But you can store that energy for a relatively long time, keeping it cooled. Now there are also differences with the interaction and laser light. So, charge these up again. And what I'll do is I'll take the infrared laser and we can see the differences in behavior. I'm going to go across each one of them at the same time. You can see that there's a dark line that forms on the cold one, and there's no change in the hot one. What's going on is when the laser hits the cold sample, it heats up the sample, and that sample is able to release some of the information, some of the light that's stored, that energy, and when it loses that energy, it remains darker. However, with a hot sample, there's not enough differential energy to release more than it's already releasing due to its temperature. So there's a point of thermal equilibrium there. No change. You'll see that it gets brighter for a little bit on the cold sample and then dims out. Our charge goes up again. I'll show you the same thing using a red laser. You'll see a similar effect. So I'll release some of the stored energy, and you'll see no change on the sample that's heated. So let's go this way. No change. So there's definitely a change of behavior, which is really interesting. And these are experiments that you can perform by heating and cooling samples of different phosphorescent materials yourself. Now, let's go and use the violet laser here. And I've got them being exposed under the 365 nanometer light at this point, so you can see the difference between the violet laser and the black light. And you'll notice that the hot sample seems to be a little lighter, which is to be expected because the laser will charge up the sample more. So if I go like this, you'll see it gets brighter. Now, if I do that with the cold sample, here's where it gets interesting. It actually gets a little darker. No, it does on the hot one too. Not as much. So even with this temperature difference, even a laser that should charge up the materials can also have that same effect where it heats up the material more and releases some of that energy quicker, leaving a darker area, even though it's one that would charge it up normally. Just take a look at the effects that a green and blue laser has on it. I'll charge up the materials again using 405 nanometer light. Here's the green laser. You see a big dark line in the cool sample and no change on the warm sample. Very different outcomes. Charge this up again. And now with the blue laser. Once again, this should charge and not remove light, so let's see what happens. And we can see that actually the blue light charges the hot and the cold samples, unlike the violet light, which discharges the blue sample, or the cold sample. So I'm going to do the violet on the top, and I'm going to do the blue on the bottom. We'll see the differences. You'll see that the violet makes the area darker, the blue makes it brighter, and it has the same effect for both the frequencies on the hot sample, where it illuminates the fluorescent material, or phosphorescent material, just about the same. I'm going to increase the heat on the hot side. What I'll do is I'll charge them up again, and we'll swap the plates. And just take a look at that demonstration of moving the plates over. I'll put the hot sample on the cold and the cold sample on the hot side. I'm going to wait a little bit. Good enough for me. Let's go ahead and swap those samples now. So I thought this was just kind of some interesting experiments, and I wanted to show you. I will be doing a more in-depth video on fluorescent and phosphorescent materials in the future, and I'll go over some of the more complicated physics in that. We get to learn about the story of electron pairs, their separation, and the reuniting of those long lost electron pair pals. That's about it for this video. I hope you enjoyed and learned something, and I do hope you experiment with this on your own. It's really interesting just to see the different behaviors with different temperatures of phosphorescent materials. Well, as always, stay tuned for more.